What's the difference between single replacement and double replacement? It's just like dating. You've got some dude over here, and he's got really long dark hair. He's super sexy, dude. I know it looks like a girl, but dude, he's a dude. I gotta finish his face here. Oh, okay. And he is hanging out. He's single. He's all by himself. So, and then we'll draw in a chick. I know I've got them reversed here, blue and pink, but that's all right. It's the way I feel today. It's early in the morning. I'm up here doing podcast during the summer. You're at home sleeping, so. And here's this chick, and she's hanging out though. She's not alone. She is hanging out with this green dude. Is not so hot. He's got one arm longer than the other. He's a short dude. He's got 3 eyes. He's bald. Single dude and couple. So you've always got a single element all by itself and a couple or a compound for a single replacement reaction. This chick is thinking, hey, can I do better? Ooh, I forgot to give the girl hair. Hang on a minute. Has to be longer than the dudes, right? And I'll give her like curls and stuff. All right. She's thinking to herself, can I do any better? Well, this guy's way hotter than her current boyfriend. So can she do any better? Of course she can. So that's what will happen. Green dude will be left all by himself. He will be replaced. And the chick here will be hanging out with dude over here. That is single replacement. In double replacement, you have 2 couples. So you've got 2 compounds. So you've got, I'm just going to draw A and B because I can't draw. And I'm going to write C and D. So what happens is they're a couple and they're a couple. And what happens is A and C just swap places. So at the end, C will come over here and live with B, and A will come over here and live with D. They just swap places, double replacement. That's the basic difference between the two. So let's go through and actually look at the rules. Hopefully for this, you've got your copy of the rules out. If you don't, go ahead and pause and go get it. All right, for this one, for single replacement, you're going to need the activity series. If you don't have an activity series, you need to go ahead and find that. It's on the back of your rules of reaction. Once you have your activity series, we're ready to go once you know where it is. Okay, the first rule, one metal will replace another metal. That hot guy will replace a lesser guy. The trick here is not all single replacement reactions will happen. So you have to think, is one element more active than another? So you always have to check. In fact, that's probably a good thing for us to write. Right up here at the top of your single replacement rules, let's write check to see if it happens, because some of them won't happen. Go ahead and write that note up there, and that'll remind you to check. If it doesn't happen, we're just going to write NR, no reaction. So let's look at one that does happen, aluminum and silver. So look on your activity series, find aluminum, find silver. Is aluminum more active than silver? Well, let's see. I know it's a little pixelated, but this is an example of an activity series. The ones we're comparing are aluminum and silver. So find aluminum and find silver. Is aluminum more active than silver? Of course it is. So it will replace it, but the reverse would not be true. So it's important to realize that they won't always happen. So that one actually happens. Rule number 2, some metals will react with water. Some metals will react with the hydrogen in water, releasing the hydrogen. So in other words, some metals will just swap places with hydrogen. So here we have sodium replacing hydrogen. Now, something important. I don't want y'all to think that all of the hydrogen goes away. What I want you to think about here is that the water looks like this, HOH. The sodium is just going to trade places with the first hydrogen. Lots of people get this wrong and they say that it makes sodium oxide. And that's not the case. We want to make the first hydrogen go away. The second one stays as an OH group, as a hydroxide. We actually make a metallic hydroxide or a base and hydrogen gas. If you look at your activity series, you can tell which ones react with water and which ones react with acids and stuff like that. And I'll show you how to label yours right now. So go ahead and get yours out and I'll show you what the little marks mean. So this is my copy of the activity series. So this first line right here, I want you to write the word water. The second line down here, I want you to write the word steam. Third line down here, I want you to write the word acid. And this last one down here, I want you to write the word oxygen. So get those in. What that means is everything above the line will react with that. So if I wrote water here, then everything above that, all the highlighted ones, will react with water. Same is true down here for where I wrote steam. Everything above it, all of the highlighted items, everything from lithium all the way down to cadmium, will react with steam. Everything from lead to lithium will react with acid, and anything from mercury to lithium will react with oxygen. So these three at the bottom we call the noble metals because they don't react with much of anything, right? They don't typically oxidize very well. Once you have that in place, you know which ones react with water and which ones don't. Third rule, some metals will react with the H in acid. Magnesium here will swap with hydrogen, and that's just a single replacement reaction. Notice it says some, not all metals will. There are a lot of metals that won't react with acid. How do you know what they are? Check the activity series. And then the last rule is some halogens are less active than other halogens. If we go up and look at that real quick, you see that fluorine is the most active and iodine is the least active. And that's true of the periodic table. Fluorine's on top, iodine's on the bottom. So that part's easy. One halogen will replace the other. This is probably one of the places where students make the most mistakes. They're always looking for some metal to swap places with another metal. So let me show you what some people do, and you will maybe write yourself a note that says, don't do that, you. But some of you guys are going to want to take the fluorine and swap it out with the calcium. And what you would make there is calcium all by itself and fluorine bromine all together. Now, that might seem reasonable to you, but realize that this guy up here, this calcium, is an ion. So he's not going to want to just leave and be by himself. And the fluorine is going to not go live with the bromine. The fluorine's actually going to swap places with the bromine. So just realize that that's true. All right, double replacement. Double replacement rules are almost useless because all double replacement reactions are virtually the same. An acid and a base yield a salt and water. Well, the hydrogen and the sodium swap places. It's just that easy. The two things out front swap places. So the hydrogen goes to live with the OH, making water. The sodium goes to live with the sulfate, making Na2SO4. Second rule is a salt and an acid yields a different salt and a different acid, which is almost useless again. You can see here the H is just swapping places with the Na. You really don't need a rule. The third rule is a salt and a salt yields a salt and a salt. Probably the most worthless rule that there is. What you can see is the metals are swapping places. The copper and the sodium swap places. That's all that's happening. So you don't really need rules for double replacement reactions. All you need is something called the solubility rules that helps you know that sometimes when you mix things together, does it make a solid or not? And the solubility rules is something we'll talk about in class. Solubility rules, you have them on the back of your reaction sheet. So it's something you need to look at, but I'll show you how they work in double replacement reactions. We don't use them at all in the first two. And rule number 1 and rule number 2, we're not going to use them because we're not worried about whether things are soluble. They are actual reactions that happen. Now, there is one important caveat to the double replacement rules. Rule 1, 2, 3, it always happens, yada, 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 but there is a oops or a but or a caveat. Some things, when you make them, fall apart. If you make carbonic acid, H2CO3, you don't write H2CO3 because carbonic acid doesn't stay around very long. It actually falls apart into water and carbon dioxide. So it's one of those, if you ever make carbonic acid, you need to show it as splitting up. Same thing for ammonium hydroxide, NH4OH. It doesn't stay ammonium hydroxide for very long. It actually splits up into ammonia gas, NH3, and water. And then if you ever have sulfurous acid, H2SO3, it will fall apart into water and sulfur dioxide. The double replacement rules always happen according to these three rules, and then you have a but, and this is the but. Well, there's another but you could know that that's single and double replacement, and if you're happy with those rules and you think you kind of have it down, we'll practice it in class.